So let me actually restart the introduction. We're very happy to have Aninda Sinha tell us about this exciting new work on crossing symmetric dispersion relations in QFT and CFT. Please go ahead, Aninda.
Thank you very much, Leonardo. So I'm very happy to be virtually in your presence, and I'm going to tell you about crossing symmetric dispersion relations in QFTs and CFTs. So hopefully my cursor is visible.
Yes.
Thank you. So here is an outline of my talk. I will begin with a very brief history of the Polyakov bootstrap, at least from a personal perspective. And then I'm going to tell you that I'll perform some quick checks, which will hopefully convince you that the new approach works. Then I'm going to benchmark the new results by comparing with fixed T dispersion relations. And then after that, I'm going to tell you about briefly about the outline of how this new crossing symmetric dispersion relation is derived, followed by some applications in quantum field theory, and then finally concluding with the derivation of the Polyakov bootstrap, Wheaton diagrams, and some preliminary work on analytic functionals. So let me begin with a brief history of the Polyakov bootstrap. So in 1974, as all of you know, Polyakov wrote a now famous paper, and it is fair to say that no one understood it. And Sava Rychkov told me a few years back that later on, even Polyakov did not understand it. And many years later, around 2015, we tried to understand it. And part of the reason was that we weren't talking to the experts. So nobody told us that the paper was incomprehensible. We went ahead and tried to understand it anyway in our own way. And then there followed a lot of confusion. I'll summarize the confusion in a bit. And the question was, is there a crossing symmetric formulation of the bootstrap? So what does a crossing symmetric formulation mean? It means that you have here the Mellin amplitude, or in the language of the conformal bootstrap, a Mellin amplitude, or in the language of of quantum field theories, is just the usual amplitude, and S and T are the either the Mandelstam invariants, or in the language of Mellin amplitudes, either the Mellin variables. And the question is that does this admit an expansion in terms of what now can be interpreted as exchange Wheaton diagrams? So the first three lines are the S, T, and U channel exchange Wheaton diagrams, and potentially contact diagrams. So this red thing with here in the second line is a contact diagram, and the question is that can there be an expansion of this kind? So this is what our interpretation of Polyakov's 1974 work was, that he was actually saying that there indeed is such an expansion. Of course, he did not cast it in this language. This was our interpretation. This was work done with Rajesh Gopakumar, Apratim Kaviraj, Kallol Sen. And this is how we interpreted it. Now, of course, the contact diagrams are in red because, of course, in his original paper, he had not mentioned anything about contact diagrams. Did not mention that these are scattering amplitudes in ADS space or can be interpreted in that language. And later on, of course, as we tried to develop this further, these contact diagrams became very important. So in 2016, in GGI, in one of these bootstrap meetings, Joao Penedones, I don't know whether he's there in the audience, he asked me a question. And following that question, my reaction was literally like this. Of course, I never had blonde hair, but you can think that my hair became white because I spent a lot of time thinking about this. His question was, you take the Virasoro-Shapiro scattering amplitude in string theory, which you know is a product of gamma functions, is the ratio of gamma functions, and you expand in terms of all STU poles. So as you know, the Virasoro-Shapiro scattering amplitude has poles in ST and U variables. And he told me that you take this and you try to expand it in all three poles. And you can do this equivalently for the 2D Ising-Mellin amplitude. And needless to say, we tried very hard. We tried very hard for many months, and it didn't work. But nonetheless, there was something that worked. We knew that the epsilon expansion worked. It gave us the correct results, which matched with the anomalous dimension results that came from the Feynman diagram approach, at least up to a certain order. And it also gave us new results about the OP coefficients. So we scratched our head for a very long time. We couldn't understand what was going on. And in the language of Mellin Bootstrap in 2018, Rajesh Gopakumar and I found that one could not ignore these contact terms, these diagrams in red. But needless to say, we did not have any clever ideas how to fix them. Dalemel and Miguel fixed these contact terms in one dimension. And this was kind of a sort of a simple problem in the sense that in one dimension, you don't have spin. And the arguments they used were somewhat different than the arguments that I'm going to tell you now. And these arguments, at least to the best of my understanding, do not extend to higher dimensions. And there was some work that I did with Pietro, Kosik, and Ahmadullah, which extended the story in Mellin space in one dimension. So later on, and this is work that has been developed over the last year or maybe a couple of years, the two Joaos and Sasha, and then Leonardo, Simon, David, and Dalemil worked out what I want to call the usual dispersion relation, the fixed T dispersion relation for the Mellin amplitude. Of course, there has been other work as well. It's not just for dispersion relations for Mellin amplitudes, but also for the dispersion relation in position space. But for the purpose of my talk, I will just focus on the dispersion relation for the Mellin amplitude. And as you know, the fixed T dispersion relation does not have manifest crossing symmetry. So this gave us a clue, and this was kind of, on hindsight, one should have thought about this earlier, that if Polyakov's crossing symmetric bootstrap idea was correct, then there must be a crossing symmetric dispersion relation. And we did what naturally everybody would do. You search the literature, and searching the literature did make us depressed for quite a while. And of course, this was in the middle of the lockdown, and this did not help us. So what I'm going to tell you about is based on some understanding that we have developed over the last year or so about crossing symmetric dispersion relations. And it's based on these two papers. The first one is with my graduate student, Ahmadullah Zahed, which revives crossing symmetric dispersion relations for quantum field theories, revives in a certain sense. I will explain in what sense. And then a follow-up work with Rajesh Gopakumar and Ahmadullah Zahed. And also there's some work in progress, which if I have time, I'll cover in the end. So let's begin with what was known in the olden days. And olden days means in the 1970s or earlier. And this predates, this was before I was born. And in fact, this 1972 is probably before many of you were born. And so the paper that I will focus on is a paper by Oberson and Khoury with the title Rigorous Parametric Dispersion Representation with Three-Channel Symmetry. This was published in 1972, and in fact, this predates Polyakov's 1974 paper, which of course dealt with conformal field theory. And this paper, if you open it and you read it, it has encouraging statements, but if you look at the formulas, none of these formulas will sort of appeal to you or strike out to you as something spectacularly useful. And the reason is that the most useful or encouraging formula in this paper was in a note added. So I guess Oberson and Khoury worked very hard, and it's a beautiful paper from the perspective of mathematical physics. They worked very hard, and they realized that, in fact, for the totally crossing symmetric case, the final representation can be simplified enormously. And other people also did some work. In particular, I should mention Mahouf, SM Roy, and Wanders from 1974. They tried to develop crossing symmetric dispersion relations for pion amplitudes. And there is some overlap between the ideas in this paper and the idea in the Oberson-Khoury paper. So let me tell you first what the formula for the crossing symmetric dispersion relation is, and then carry out some checks, and then I will show you how this is derived. So you have a fully crossing symmetric Mellin amplitude. So this could be an amplitude in quantum field theory. We will get to the Mellin case later, but this is just a quantum field theory amplitude. Let's focus identical scalars so that there is all three channel symmetry. So the statement is that the amplitude has this representation, which is in the box. So there is, because of the fact that we will assume that these are twice subtracted dispersion relations, there is going to be one unknown, which is alpha 0. It is related to the value of the amplitude at S1 equal to 0 and S2 equal to 0. So my variables are such that S1 corresponds to S1 equal to 0 corresponds to S equals to 4/3 in the usual Mandelstam variables. And I will work in terms of S1, S2, S3, which sum to 0. This is for a scalar of mass m, but I've just shifted the variables. That's all that I've done, and this shift is going to make the formulas appear nicer. So this formula tells you that you have to take the absorptive part of the amplitude. So A, this curly A stands for the absorptive part of the amplitude. So this is just the S-channel discontinuity. And there is something funny that you do. You actually, instead of just replacing T with T, you replace T with something else. And I will explain what this something else is. And this is part of the important stuff that goes on. And then there is a kernel. And the kernel has a very nice form. The kernel looks manifestly symmetric. So S1 prime is the variable that is getting integrated over. S1, S2, S3 are the analogs of ST and U. So this is manifestly crossing symmetric. The important thing is, what is the analog of T? So this is what S2 plus is. So S2 plus takes on a somewhat funny looking expression here. So it depends on the integration variable, but in particular, it also depends on the crossing symmetric combination A, which is a ratio of S1, S2, S3, the cubic crossing symmetric combination divided by the quadratic crossing symmetric combination. So I will explain later on how this comes about. But this representation is manifestly crossing symmetric because the kernel is manifestly crossing symmetric. And the only other way that S1, S2, S3 appears is through this combination A, which is a ratio of crossing symmetric combinations. So is this clear? So if there are any questions about notations, it's a good idea to ask me now. Otherwise, I will continue.
Yeah, can I ask a question? So
yes, Joao, yes.
So the H, as you said, is very nice, shows explicitly the non-analytic behavior in S1, S2, S3. But what about the A? Do you have like extant non-analyticity in the variable A?
Excellent. Yes. And that is going to play a very crucial role. You will see how. Yeah, it will, and you will see what the implications are. You are saying that okay, S1 prime minus A. It appears that if you have say polynomials in S2 plus, it will appear that S1 prime there'll be some pool or apparently some singularities corresponding to S1 prime equal to A. Yeah.
For example.
Exactly. Yeah. But those are going to be very important. Yes. So let's first, before I go into the derivation of this formula, let me just carry out.
Sorry, a trivial question. You're assuming that the original amplitude is crossing symmetric.
Yes. So this is for identical scalar scattering for concreteness. Yeah. Any other questions?
So would there be a generalization to a non-crossing symmetric amplitude that sort of treats all the channels in a
yes.
More
in fact, in this Robertson-Curry paper, they do write that out. For the pion case, it's a little different. It works a bit differently. So this is what is done in Mahut's Roys and Wonders. But in fact, you can treat various channels differently. This was done there. The simplifications, the beautiful, nice formulas, the compact expressions that we have works for the totally crossing symmetric case. Yes. Okay. So let's carry out some sanity checks. So let's carry out the check for Joao's question. So this is Joao asking me the question. So this is a beautiful picture. I love this picture because the similarity with Joe is incredible. So this is Joe screaming his question at me. No, he's too nice.
Sorry, where is that from?
It's Google. I don't know. I've had it for a long time. So, but nonetheless, I mean, so no, Joe did not scream his question at me. He asked me in a very, very nice way. It's a very legitimate question that you take the dilettante scattering amplitude. So I have dressed it up with, I've just dressed it up with an additional factor so that there is no massless pole. So this is the usual dilettante scattering amplitude, and there is a kinematic prefactor as well, which I'm not interested in. But it's a nice function. It has infinite number of poles. It's crossing symmetric. So let's try to expand this using that formula. So when I tried this, in fact, I tried very hard before we came, we played around with this new version. Literally, we tried for a long time, and it's a very nice mathematical physics question. That can you expand this in terms of just the poles in the three variables? So there's S1, S2, and then S3 is minus S1 plus S2. And you try to expand them, write it as a residue over the S1 poles, residue over the S2 poles, residue over the S3 poles, sum them up, and you will see that it does not come anywhere close to the actual expression. Whereas if you did the other one, that if you just expanded in terms of the S1 pole and the U channel, the S3 poles, then it gives you a reasonably nice representation. So this is the first thing that you would naively try, that you just take the residues, you just sum up the poles. And this does not work. This is very easy to demonstrate. It's a one-line calculation in mathematics. But if you just do the SU channel poles, it works. I mean, of course, the question that we are trying to find out is there a representation of this kind where you have all three poles, all three channel poles, multiplying by something that is manifestly crossing symmetric, and maybe there is some constant piece here as well. So the answer to Joao's question is the following. So you have this crossing symmetric expression, it's a ratio of gamma functions. It admits an expansion, which is manifestly a sum of all three poles, times some hideous looking ratios of gamma functions. Now, of course, this part comes from the kernel H, which I showed you. And this is, of course, manifestly crossing symmetric. The products of gamma functions is also manifestly crossing symmetric because the dependence on S1, S2, S3 enters through A, and A is a ratio of these crossing symmetric combinations. So I think it's become sort of conventional that you call this cubic object Y and the quadratic crossing symmetric combination X, and that's what I'm going to do up to a sign. So I think the cubic combination is minus Y and the quadratic combination is minus X. It doesn't matter. So A is Y by X. And there is a sum over K because there is an infinite number of poles. So you have to sum over all of them. And you can check very easily that it gives you a very nice representation. You ask where on the real S1, S2 plane does this representation give you a 10% agreement with the actual answer? And you will see that it gives you a 10% agreement in a lot of region. And you can also ask where does the two-channel representation or the fixed T representation give you a nice agreement. That gives you an agreement somewhere also. And there's some region where they overlap. There are also regions where they don't overlap. And you can do some other explicit checks. You'll see that the agreement is very nice. It agrees very well with the exact answer as well as the crossing symmetric answer. And the known answer. And similar expansion exists also for the 2 de-Ising-Mellin amplitudes, because here we are, of course, we are just taking the discontinuity, and we are expanding. We are not decomposing in partial waves as yet. We are just taking the discontinuity and expanding. And you can do further checks. You can ask how quickly do things converge. You can truncate the K sum. You can make S and T complex, and then the agreement seems to be very, very good for random sampling of values as well. So this was a sanity check, but notice that something is non-trivial. So just consider a fixed case. So say one of the terms in the sum. So here. And let's consider expanding around a equal to 0. So why a equal to 0 is a nice point to expand around, I will come to later. That comes because of the fact where the partial wave expansion converges. But let's suppose we expand around a equal to 0. So a is a ratio of y over x. So suppose you consider a power of a, it will look like some power of y and some power of x, but x will be in the denominator. So for a fixed k, you will find that if you expand around a equal to 0, you'll start getting negative powers of x. So this is for a fixed k. Now on the left-hand side, this guy, the amplitude that we started off with, did not have any of these negative powers. So what must be happening is that once we sum over k, these negative powers will cancel. And this is an important part. This will play a crucial role. This will also have an equivalent condition in the fixed T dispersion relation. I'll come to that. It's not as if things are not understood. But this is an important thing, that you will get negative powers for fixed K, and in the full amplitude, these are not there. So the lesson is that to have a crossing symmetric expansion, it seems that we have to introduce spurious or non-local singularities to the basis elements. And I should point out that these have nothing to do with Polyakov double poles in the context of CFTs. I mean, that will come later.
So what does this mean for the Reg behavior of each?
Okay, I will come to that. It's a good question. So each K is actually Reg bounded. You'll see how. Yeah, so it's a good question. Yeah, I will come.
Why did you have to factor out the massless poles? Can you also do it including?
Yes, I think you can put in the massless poles in some limit. So because the representation, I started by saying that the integration started from 2 mu by 3. So this is like 4m squared to infinity. So if m goes to 0, the integration starts from 0. And then if you don't do it in some regularized fashion, then you'll get an infinity in the integral. So, but I think you can put in a regularization. I was trying that out. In fact, if you put in a regulator and do it, it will still work.
So you say
by that I mean that if
there's another version of the representation where the sum starts from k equals 0 and you go, or from
so it will start, the integration starts from 0 or maybe epsilon, and then you take the limit epsilon going to 0, and suppose you wanted to do 1 over s1 s2 s3. So this is the usual thing that you would be interested in. Yeah, so there is a version where you can reproduce 1 over s1 s2 s3. So the way that you do it is you start with 1 over s1 minus a times s2 minus a times s3 minus a. So a is this a and this a are not the same. So s1 minus alpha, say s2 minus alpha, and s3 minus alpha, and then take alpha to 0 at the end of the calculation.
And another question. So you showed this numerics of region of convergence. Do you understand the region of convergence of this sum?
Yeah. Yes. For quantum field theories and conformal field theories, we do understand. I will come to the different cases. I will mention the different cases later. Yes.
Thank you.
Yeah. Okay. So you can have a crossing symmetric expansion. It does have this form that you would have naively thought that it has the 3 channels, but then the coefficients are reasonably complicated, and you have to understand what this means. So before I go to deriving, let me benchmark using the results of the fixed T dispersion relation. And I will primarily, so there's been a lot of work. So two Joao, Sasha, Simon, Dalimil, Leonardo, David, a lot of people have contributed. And in fact, in quantum field theory, there have been some very important pieces of work in recent times by Simon and Andrew Tolley and company. So I will mention some of this as well. And I think there's some overlap there as well. So I will benchmark that. By that I mean that I'm going to I will first summarize what is known about the fixed T dispersion relation, and then I'll make a comparison when the time comes. So these are my Mellin conventions. So I will work in these S1, S2 variables. So if I'm talking about a conformal field theory, this is the usual correlator in position space. It has a Mellin representation. M is the Mellin amplitude. Mu is the measure factor which carries information about the double poles. And of course, I will not have anything to add to the story that Sasha and Joao developed. I will assume that there is such a representation. And so there are two kinds of sum rules that I will focus on. And there are versions in the literature, but the papers that I'm going to compare are these two. So there are two kinds of sum rules. The first kind, which just follow from crossing symmetry. You're not imposing any Polyakov conditions. And these are the sum rules that are mentioned in this first paper, this long paper by Joao and Sasha and Joao. And the second kind of sum rules are which follow from the Polyakov conditions. So let's begin by reviewing what one meant. So one means that you have a representation, you're writing down a dispersion relation of this kind. And then you put in the conformal partial wave expansion. So when you do that, you will get a representation like so. And then you have to check for crossing symmetry. So you have to impose a condition that M at S1, S2 is the same as M as S2, S1. So this is a condition, this is a crossing symmetry condition, and this crossing symmetry condition you can expand. You can expand around S1 and S2 equal to 0. You'll get an expansion of this kind. And so you will get some rules corresponding to curly E, subscript PQ being equal to 0. So one kind of sum rule was mentioned in this paper. I'm not sure if the fixed dispersion relation, at least so far as Mellin amplitudes are concerned, have studied a generalized version of these sum rules. And Joao can tell me if the story has developed any further.
So I think it's a fair description. Yeah.
Yes. So curly E is the crossing symmetry sum rules. Just remember that it's a fixed dispersion relation. You're imposing crossing symmetry, you get some curly E. So curly E equal to 0 is one kind of thing that we will have to deal with. And in fact, even in quantum field theory, so although I'm talking about the sum rules primarily because I'm keeping in mind that I want to derive Polyakov's bootstrap, and there is in fact a similar story also in quantum field theory. So in quantum field theory, what you would do is that you would, instead of this conformal partial wave expansion, you would have a partial wave expansion in terms of Gaussian-Bauer polynomials. And the analog of these constraints are what Simon and Duong call null constraints in the context of effective field theory. So in fact, just bear that in mind that there are these analogs also in quantum field theory. The second kind of sum rules, which actually give rise to more interesting sum rules because one can have positivity on the analytic functionals and so on, are what follow from Polyakov conditions. So there are these non-perturbative versions of the Polyakov conditions which are explained beautifully in this paper. For my purpose, I will just say the Polyakov conditions follow by demanding that there are no operators with scaling dimension exactly 2 delta phi plus L plus 2n. There are, in any quantum field theory, typically these get anomalous dimensions, so these are not there generally, and that gives you some conditions. So this will give rise to
in our paper we demonstrated that this is not an independent condition; it just follows from crossing.
Yes. So I guess you're saying that you have a similar version. So all that I will use is that there are these sum rules which correspond to little omega, which actually.
Yeah, but you need to assume nothing about the spectrum. That was the point of our paper. That
okay. Yeah. Sure. Sure. You can say that at these special points. Which correspond to, I mean, in the original variables, which correspond to S equal to delta phi plus n, your Mellin amplitude vanishes. So that is similar to what you have in your paper as well, right?
Yeah.
Yes. Yeah. So because I wanted to actually set the notation, in fact, I will compare the sum rules that we get from the crossing symmetric dispersion relation with these little omegas. That's why I wanted to use the notations that these folks here used. So they use a contour integral over the Mellin amplitude weighted by some function. And these would be 0 because of the Polyakov condition. So the only thing notationally that you have to remember is that I had curly E and I had little omegas. And curly E was followed from imposing crossing symmetry on the fixed T dispersion relation, and little omegas followed from the Polyakov condition. So one thing I should mention is something about locality. So locality in some, maybe in some loose way that I'm using, but in the fixed T dispersion relation, locality in the following sense is inbuilt. So suppose you use the fixed T dispersion relation and you expand in the partial wave expansion, then you can see that you will only get positive powers of S1 and S2 appearing on, when you expand, assuming that there's a mass gap. So I'm assuming there's a mass gap in quantum field theory, and also there's some twist gap in conformal field theories. But basically, you will not see any negative powers of X appearing in the expansion around S1 equal to 0, S2 equal to 0. So this is, loosely speaking, what we will refer to as locality. So basically, the fixed T dispersion relation has locality inbuilt, but we impose crossing, and that gives you these curly E conditions. And you'll see how things change when we use the crossing symmetric dispersion relation. So is that kind of clear? I mean, is there any question about this statement? Okay. So let me briefly derive the crossing symmetric dispersion relation. I will follow Oberson and Khoury, but the algebraic details can be found in my paper with Ahmadullah. I think Oberson and Khoury sort of gave a telegraphic version because the most useful form of their dispersion relation is given in this note added. So you have to fill in the blanks. So the key idea is that suppose we have a completely crossing symmetric amplitude, and if there are no massless poles, we can expect that your amplitude will have an expansion or admit an expansion in this form. So let's focus for the time being on quantum field theories, and there will be a similar story also for Mellin amplitudes, but let's focus on quantum field theory. So you'll have an expansion in powers of X and Y. So X was just a quadratic combination of Mellin variables, and Y was the cubic combination. These calligraphic W's are referred to as Wilson coefficients. The idea of a dispersion relation, crossing symmetric dispersion relation, is that we consider a cubic equation. And this was the A that I was using in the demonstration that the crossing symmetric expansion works. So this is a cubic equation because, well, it's obviously cubic. And this cubic equation, so S1 plus S2 plus S3 is equal to 0. This can have this following very useful parameterization in terms of a new variable Z. So you can show that this you can parameterize a solution for S1, S2, S3, which solves this cubic equation in this manner. Sk is A minus A times Z minus Zk cubed divided by Zq minus 1. Zk are the cube roots of unity. It's a fun exercise to do. You can just put it in, and then you will see that it gets satisfied. And it also satisfies S1 plus S2 plus S3 equal to 0. So the thing is that we will go to the complex Z plane, and the way that we are going to derive this crossing symmetric dispersion relation is to write down a dispersion integral in this variable Z, keeping A fixed. So that's the key idea. So this is what the complex Z plane looks like. So Z1, Z2, Z3 are the cube roots of unity. The cuts, the S channel cuts and the T channel cuts and the U channel cuts are indicated here. So the red arcs actually tell you what the cuts are. And if you were interested in the limit where S1, S2, S3 went to 0, then you would be zooming into the origin. But if you were interested in the Reger limit, where you are taking one of the variables fixed and taking two of the variables to, well, the mod of the two of the variables to infinity, then that would basically translate into going to one of these regions, Z1, Z2, or Z3. And that's kind of important to note that the Reger limit basically translates to taking S1, or, well, I mean, the fixed T language S2 to A and S1 and S3, mod of them to infinity. Okay. So you can just do this in your head if you want. And there are, depending on what the range of A is, the structure changes somewhat. So in fact, there are ranges of A where the gaps close up, and so the arcs close up, and then that would essentially mean that you'll have to find different analytic continuation from inside to the outside.
What about Z equals infinity?
Z equal to infinity is just S goes to 0. So in fact, strangely, Z equal to 0 and Z equal to infinity map to the low energy region. Yeah. Okay. So yeah, so in the original crossing symmetric dispersion relation, you remember that there was this S2 plus. So instead of T, we needed to put S2 plus. So where does that come from? So now it's very easy. So if you substitute S3 to be minus S1 minus S2, you'll get a quadratic equation for S2. And that is what gives you this. There are two roots, S2 plus and S2 minus. And that's what gives you the S2 plus that you saw in the original formula. And it doesn't really matter because we are considering identical scalars, so it doesn't really matter whether you're using S2 plus or S2 minus, you'll get the same result. Is that clear? So how you got this S2 plus in the original equation. So you'll see how S2 plus enters also, because soon we will write down a dispersion relation in the usual way. So now we are going to write down a dispersion relation in Z for fixed A. So just as an aside, because it'll simplify some of the algebra, this original Y variable, which was a cubic combination of the S1, S2, S3, has this very nice expression. It's A cubed, and you have Z cubed over Z cubed minus 1 square, and X has a similar expression. Instead of A cubed, you have A squared, and same dependence on Z. So basically, if you have a fully crossing symmetric amplitude, and then in terms of E and Z, it translates it into an expansion in terms of E and Z cubed. So that's the operating word, that instead of just being a function of Z, it's Z cubed. So when we write down a dispersion relation, we have to assume something about the amplitude. So conventionally, because of the fact that people had proven the Frossard bound by then in the 1970s, and then the Frossard bound together with the Feynman-Lindelof theorem tells you that the Mellin amplitude for fixed S2 should go like little o S1 squared. So it shouldn't go as S1 squared, it should be below that. And similarly, you will have this kind of a behavior for the other channels. So as I said, this is the Reger behavior. So this translates into taking limits. You have to approach Z going to one of the cube roots of unity, depending on which variable you're taking to infinity and which variable you're keeping fixed. So okay, so if M goes like 1 over z minus zk square, then you can see that in order to write down a dispersion relation, we have to multiply by z cube minus 1 so that this dependence is overcome. So now you do this do what you would expect, that you will write down an integral over this large arc, and then an integral within the circle, and then take them to approach each other. So the outside arc is going to give you an equation like this, and the inside arc is going to give you an equation like this. It's not very difficult to verify, but then basically now you're going to take the difference between the two. And once you take the difference between the two and you go back to the original S1, S2, S3 variables, remember that we had this parametrization S1, S2, S3 given in terms of Z in this manner. So you can go back to the original variables. Takes a bit of algebra, but basically after the algebra, you'll get this representation. So let me just pause there, ask you if there are any questions. Do you have any clarifications regarding the derivations? Of course, I'm skipping some steps, but then it's not very difficult to verify them.
Could I ask you to comment a little bit on the region where we check unitarity? So where is it in the figure? The region S bigger than 4m squared and the angle between 0 and pi?
So yeah, so yes. So the S channel will be a combination of these two arcs. A portion of this arc and this arc will be the original S bigger than 4m squared. Okay.
So it converges in the full region where we will check unitarity. Any S bigger than 4m squared. There is no upper limit. I vaguely remember at some point, but I'm probably confusing that there was an upper limit. But
so are you talking about the dispersion relation for partial waves? So partial waves actually have an upper limit for S. So there are these something like 60 m pi square or something like that, below which they have the representation converted.
Yeah,
so
probably
that is for the partial wave. That is for the FL as a function of S when you're writing down a dispersion representation for that.
Okay. So if you were to impose unitarity for those, you could only do it between 4 and 16.
Yeah. Yes.
I see.
Yeah.
But sorry, Aninda, I didn't understand this comment. I mean, if you have we have a cut in S from 4m squared to infinity, and we evaluate the function on top of the cut, for example. So now you say this cut becomes two cuts in this picture. I didn't understand. Where is it, say 4m square maps in this picture?
So S bigger than 4m square maps into these two regions. So there are portions of this upper arc, and then there is a portion of this arc. Okay. So the U channel cut is going to get mapped here, and the T channel cut is going to get mapped here.
So it's kind of just, it's but it's the same information on both cuts, you say.
Yeah, that's right. So because of the fact that you're using this parametrization, so the way that you would find where the cuts map is just ask the region of Z such that S is bigger than 4m square, and that's what you do. Yeah.
I see.
Mm-hmm.
Hi, I have one question.
Yes.
The usual fixed T dispersion relations, this 1 over T minus T prime has a group theoretical meaning in terms of P times Q, like P polynomials and Q polynomials sum over spins. Does this also have meaning like that?
Which one are you? So sorry, I didn't.
So 1 over T minus T prime has a group theoretical meaning in terms of sum over spins.
Okay.
Pjt times Qjt prime.
Yes.
Does this dispersion kernel has a meaning in terms of group theory in that sense?
I have no idea. Could be. I'm not sure. Yeah.
Thanks.
Aninda, can I ask you a different question? So when you do the dispersion relation, you're closing. I mean, usually we need the Regge limit because we want to drop the arc at infinity.
Yes.
But here you have just an integral around these finite arcs. The question is if you can collapse the integral all the way around that point. Is that
that's right? Yes.
Points? That's why you need the subtractions.
Yes, because if you remember, the Regeer corresponded to some behavior of this kind as you go to the cube roots of unity. So you wouldn't be able to go all the way if you.
But if you leave like a small arc integral around that point without really collapsing all the way to the point, it will be fine, right?
Yes, that is true. I mean, if you.
But then it was difficult to imagine complex singularities in the S-plane. That's what you're saying.
I would guess so. So you're saying that, yeah, how would you do that? So you probably require to draw an arc all the way around this and then avoid this point, each of these points. Yeah.
It's okay, I think.
Yeah. I mean, I should say that, I mean, of course, you could make this condition weaker, and we know how to make this condition weaker. So ultimately, we came up with this beautiful kernel, and this kernel actually looks like you have performed some subtraction because of the fact that you have an S1 here. So you could have split this up as 1 over S1 prime minus S1 plus this, and then minus 3 times something. So there's a constant piece like that. So instead of this does not appear to be the simplest kernel that you could think of, which is crossing symmetric. The simplest kernel that you could think of is when S1 is replaced by 1, S2 is replaced by 1, S3 is replaced by 1. So that would actually correspond to needing a fall off here, which would go like a constant and not 1 over z minus zk squared. So I think we could have other interesting kernels, and that in fact is an interesting exercise to work out. So what other kernels can you find from this approach? Yeah.
So I had a question on about your previous slides. The one, here. As S1 varies from threshold to infinity, it looks like S2 is always. Well, I want to ask what S2 does. Like, where in the ST plane, what is the integration line in the ST plane? If I were to take, for example, A to sit in the Euclidean region, or A for physical.
I had a picture for that. So that's a good question. So in fact, Oberson Khoury draw the things in the Mandelstam plane. So it looks like an arc that surrounds the, the Mandelstam diagrams. So you have these physical regions. So it looks like an arc that surrounds the physical S, physical T, and physical U regions.
It's never inside those regions. It's just around. It goes around.
No, it could also be inside those regions, but that depends on what range of A you're considering. So here, the diagram that I drew was for a particular range of A. So I did not explain where this formula came from, and then this actually is important to have these gaps. Yeah.
I think from the slide that you just showed, if you pick A equals 0, I think it's fairly simple, right? Then S2 is 1 over 2. And then I think you get a straight line that seems to just lie entirely in the physical region.
Okay.
If I'm not mistaken. I was wondering, in particular, if it goes to like these more mysterious regions where S and T are both greater than 4, for example, where we don't quite know what the amplitude does.
Right.
So I was wondering for which values of A it would go inside that region.
Yeah.
Yeah. Then I also don't know how many subtractions, for example, you would need.
Yeah. So the viewpoint that we are taking is that we are going to work in a we are going to work in a region of A, which allows for the partial wave sum to converge, and then we are going to. So as you can see, that A equal to 0 is in this allowed region, and then we are going to get interesting constraints by expanding around A equal to 0.
I see.
Yeah.
Okay, thank you.
Okay, so once you have this this nice formula, what can you do with it? So one thing is that now you have a crossing symmetric representation of a crossing symmetric amplitude. So both sides are crossing symmetric. So this means that we should be able to write down an immediate formula for the Wilson coefficients. So let's consider quantum field theory. Let's write down the absorptive part in the usual partial wave expansion. So this is how you usually write down. This is the Gegenbaur polynomial, except that instead of cos theta, you have this complicated function, which is inherited from the S2 plus dependence in the original formula. So don't have to pay any special attention to this square root of psi. The only thing that I should point out is that you will, like what I said in the example, the explicit example for the string amplitude, when we expanded, we saw that, you know, the coefficients, if you expanded around small a was y over x, and then if you had polynomials in a, you would get negative powers of x. So you'll have that kind of behavior even here, and we will deal with it. So yeah, so one comment here, which I should read out, is that the partial wave expansion is convergent in the Lyman-Martin ellipse. So in my notation, it translates into a being between these two values. So in particular, if you just blindly took mu to 0, then you would get a 0 radius of convergence for a. So a would be literally 0. So once you have that, and in fact, it's a very easy exercise to do. You just have to match powers on both sides. You get a very nice formula for the Wilson coefficient straight away. I mean, it's not a sum over Wilson coefficients, it's just each Wilson coefficient. And you get a nice integral representation of this kind in terms of the absorptive part of the partial wave amplitudes. And instead of, so if you are familiar with fixed T dispersion relations, you typically see derivatives of the Gegenbaur polynomials or derivatives of the Legendre polynomials entering these formulas, these kind of formulas. So instead of that, you have some finite sum. So this is always a finite sum. All these summation is finite of derivatives of the Gegenbaur polynomials. So explicitly you will see derivatives of the Gegenbaur polynomials, but with respect to this somewhat more complicated dependence because of this square root of psi that is sitting here. But essentially, I mean, it's a formula that you can just put in Mathematica, and you can study various properties of these curly B functions very nicely. It's not a big deal. Now, one thing is that in the way that I'm writing this down, if you follow the math a little bit, it's quite easy. It requires a bit of staring, but then you can actually see that you can have. So the way that we define the Wilson coefficients are the second. This m here is associated with the power of y. And the first entry here is associated with the power of x.
So remind us a bit, which one was x and which one was y? Sorry.
So x was the quadratic combination and y was the cubic combination.
Yes. Okay, thanks.
Yeah. So because of the fact that we are expanding around a equal to 0, you will see negative power. You can potentially see negative powers of x, but you'll never see negative powers of y. So our formalism is such that m is bigger than or equal to 0. But however, this first entry, n could be less than or equal to m, which would allow for negative powers of x. And we have to assume something about locality. So if you assume that there are no such negative powers of x in the low energy expansion, then you would get a constraint. You would say that some quote unquote locality constraints would get rid of these negative powers of x. And these are new constraints. But they're going to get related to the fixed T dispersion relation constraints. These curly E are basically these constraints. And these new constraints are such that they exist only for n bigger than or equal to m, because then the first entry would become negative, or I mean n bigger than m rather. I mean, this is not bigger than or equal to m, n bigger than m. And another feature is that in these locality constraints or null constraints, whatever name you want to put, we prefer calling them locality constraints, only spins bigger than 2n contribute. So that's kind of an important thing to remember, that If you look at these constraints individually, you change n, then as you change n, n equal to 1, spin 2 contributes, n equal to 2, spin 4 contributes, from spin 4 onwards contributes, and so on. Okay.
This is actually m greater than n, not n greater than n. You have written it.
Sorry, yes, you're right. Thank you. Thank you, Amadullah. Yeah, so there is a printing mistake here. It should be m bigger than n. Sorry, thank you. Yes. Yes, thank you. So, okay. So now let me change gears. So there appears to be two kinds of expansion. So I will use the nomenclature Dyson block expansion. I want to name it. I have to call it something. I can't call it that. This is the expansion in terms of the massless pole subtracted amplitude in terms of crossing symmetric partial waves where locality constraints are implicit. So if I continuously use those set of words, it would take me the whole night to finish it. So let's call this the Dyson block expansion. So this means that we are just expanding in terms of this kind of an expansion where there could be these negative powers of x. Maybe when you have a physical spectrum, when you sum over the physical spectrum, the negative powers of x will cancel. But individually, for each L, there could be these negative powers of x. So that kind of an expansion I will call the Dyson block expansion. So you can do the same game that we played. So you take the string amplitude, you do this partial wave expansion, you subtract out the massless pole, and you plot the fractional deviation. So fractional deviation means that you truncate to spin 6 and also the pole number of poles to 6. And then you ask what is the fractional deviation from the exact answer. And as you can see, the fractional deviation is extremely tiny. At least in the region that we have looked at. But the more interesting expansion is what I would like to call the Feynman block expansion. And this is where I am taking each block and operationally, I'm throwing away the negative powers of x at the level of each block. Why am I doing that? It's because that once we impose these locality constraints, the sum over the spectrum of these negative powers are going to cancel. So operationally, what I'm doing is that I'm taking each partial wave times kernel, and I'm throwing away all these negative powers. And I get a similar good agreement. Again, it's for the same number of spins and same number of Kmax, and you can compare. And it does appear that the Feynman block expansion, which has these negative powers removed, appear to behave better. Again, this is one data point. I'm comparing with the string, the dilettante scattering amplitude. So of course, you could say that, oh, this might be just a coincidence, but nonetheless, this is just a proof of principle that it seems to work, that you could try to think of it as an expansion in terms of what the original formula gave us. But the original formula also told us that there are these, each block-wise, there are going to be these negative powers of x, and you get these new null constraints or crossing symmetry constraints on the physical spectrum. They are not going to be there. So you could decide to expand in terms of these Feynman blocks which don't have these negative powers to begin with. So what is the structure of the Feynman block? So I want to do this at the level of the quantum field theory because at the level of the Mellin amplitude, the story is going to be similar. So this is what I would call the Regge block expansion, and the Dyson block expansion. And the Dyson block expansion is in fact Regge bounded. Why is it Regge bounded? Because in the Regge limit, if you look at it from the original variable's point of view, the Regge limit was such that S2 went to A. And of course, the kernel was bounded. So that is the reason why this is Regge bounded manifestly. In terms of the Feynman block expansion, so all that I'm doing is I'm taking this and I'm throwing away these negative powers. And throwing away these negative powers of x is not straightforward. It is not as if you throw away some poles or some poles that appear in the Gegenbaur polynomials, because you have to expand what is coming from the kernel as well. So when you do that, then you get the correct answer. But basically what you will find is that the Feynman block looks like there are these exchanges, poles corresponding to exchanges plus some polynomials, which exactly has a structure that you would have expected from the Polyakov bootstrap.
Sorry, you're probably going to explain this in a minute, but
yes,
just to get a quick sanity check. So when you're going to uplift this to conformal field theory,
Yes.
Is it going to be the Dyson or the Feynman block that will become the Polyakov block?
It is going to be the Feynman block that, sorry, I will explain the nomenclature. Excellent point. So let me explain the nomenclature. It's a beautiful question because it's properly timed. So this is what I propose as the nomenclature, because I have to go with something. I think this is a sensible nomenclature to use. So the partial wave with singularity, which means that which allows for negative powers of x, is what I'll call Dyson block. And the conformal partial wave, which has these negative powers of x, I will call the Polyakov block. So these are the Regge bounded Polyakov block, if you want. Okay. So these guys, the first line is Regge bounded. The second line, where actually I'm removing these negative powers of x, on the in the quantum field theory side, I want to call it the Feynman block, and in the conformal field theory side, we should call it the Wheaton block, because they represent the Wheaton diagrams. Okay, so if you have any strong disagreement with this nomenclature, we can discuss. But I mean, yeah. But yeah, I mean, it's something that I think it's a nice nomenclature to use. You can distinguish between various things. I mean, if you have any strong objections, I'm happy to listen to them. Okay. So actually, I'm doing very badly with time. So, but let me just very quickly tell you a couple of applications in quantum field theory, and then I'll tell you about the derivation on the conformal field theory side. So, as I said, you get these nice formulas for the Wilson coefficients, and then the conditions for the Wilson coefficients, inequalities, for example, maybe linear combination of these Wilson coefficients satisfying some inequalities. Those get translated into properties for these curly B's. And so basically you have to be patient and then look at properties of curly B's. You can derive a bunch of nice inequalities. So one thing that you can do is that instead of integrating from the cut to infinity, you can just integrate from some other cutoff to infinity. So this will become the Wilson coefficients in an effective field theory. Then you can show that these Wilson coefficients satisfy nice inequality. Linear combination of these Wilson coefficients are bigger than 0. And we worked out a recursion relation for these chi's. So we have a, you give me a value of n and m, I will give you the chi's which respects this condition. And basically one of the advantages is that you can look at various non-trivial limits for these inequalities. So in the limit where n was much bigger than m, which means that the power of x was much bigger than the power of y, you'll get a non-trivial inequality of this kind that the Wilson coefficients have to satisfy. And you can now test it with the dilettante scattering amplitude. So one game that you can play is that you look at the low energy expansion. You look at the low energy expansion for this massless pole subtracted dilettante amplitude. So this is, for example, in a recent paper by Michael Green and Chong-Kao Wen. It's known for a very long time. I'm just quoting a recent reference. The dilettante amplitude has an expansion of this kind in terms of x and y. So there is this massless pole, 1 over STU. And then there is a systematic expansion where you have zeta functions appearing. And suppose you were given the first few terms in this derivative expansion. Then by looking at these first few terms, can you actually locate where the first massive string state would be? And in fact, you can do that. These inequalities actually enable you to locate the first massive string state. In fact, they converge very, very quickly to the correct value. So the correct value is 1. And in fact, these inequalities tell you that within a few derivative orders, it converges to 1 very, very quickly. So we can also compare with some of the recent works in quantum field theory. So I was telling you that these locality constraints are these analogs. On the quantum field theory side, there are these null constraints. This is a nomenclature that Simon and Duong used. And these null constraints are important because they give rise to these very beautiful two-sided bounds for these Wilson coefficients. And also we examine these null constraints or locality constraints from the quantum field theory side, and they appear to give you a generalized Frossard bound. So generalized in the sense that they give you an inequality for the total scattering cross-section, which appears to be valid for any energy, not just at the high energy limit. So this is something that I don't have time to go into. But let me just, in the last 5 minutes or so, unfortunately, I've gone over time. I apologize. Let me tell you about the derivation of the Polyakov bootstrap. So this is basically the key finding, that if you consider the fixed T crossing constraints or the null constraints, whatever you want to use, and the Polyakov conditions, and I'm using this direct O sum, so that means that you have to impose both of them, then whatever we find from the crossing symmetric conditions appear to be the same if you impose both. So here you have to impose the locality constraints and the Polyakov conditions. So let's go through this very quickly. So you have a conformal partial wave expansion, and we said that there are these curly E conditions. I was referring to these crossing conditions that Sasha and Joao wrote down. These are precisely our locality constraints. And you can actually look at the locality constraints, and you can, in this expansion S1, S2, you can identify these curly E's with whatever we get from the locality constraints. And very briefly, some details. So instead of, so there were these little omega sum rules that we had in the fixed T dispersion relation. So in order to reproduce those sum rules from the crossing symmetric approach, we define a new quantity. So this capital omega is what follows from the crossing symmetric dispersion relation. This little omega follows from the fixed T dispersion relation. And then when you do this expansion, you will find that there are trivially some of these conditions that are automatically equal. And then there are some other conditions which become equal only when you impose the locality constraints. So I'm very sorry, but I did not have time to explain where this comes from, but there is also an analog where the conformal partial wave expansion converges. So there is some range. And in fact, this actually also explains why you cannot use these kind of things to do a conformal partial wave expansion for the 2D Mellin amplitude without doing subtractions. 2D Ising Mellin amplitude, 2D Ising Mellin amplitude without doing subtractions. But nonetheless, these crossing symmetry conditions, or the curly E conditions, have some nice properties which we have been examining over the last few days. And although they don't have a priori nice positivity conditions, they still have some nice properties. So where does this original picture, so there was this original thing that I said that there is going to be this exchange Wheaton diagrams plus contact diagrams. Where does all this fit in? The question is, in the purview of the crossing symmetric dispersion, can we expand in a basis where the locality constraints are inbuilt? And the answer is yes. And these are what are the Wheaton blocks. So I showed you what happens in the quantum field theory side, what I call Feynman blocks. And in fact, the Wheaton blocks are such that all these L greater than equal to 2 contact terms are fixed. So we explicitly worked out up to spin 10 contact terms, L equal to 2 and L equal to 4 contact terms are explicitly worked out in our paper. So we are trying to, so we have the algorithm to generate any order contact terms. We are looking for a closed form expression for these contact terms. We have not managed to find it so far.
Sorry, if I get your nomenclature, so this would not be Reggie bounded.
These would not be Reggie bounded. That's correct. Yes, that's right. These contact terms, of course, have the desired form. So this is the desired form. If you demand effective field theory, this beautiful paper, Heemskerk, Penedones, Polzinski, and Sully. And of course, this is what we conjectured should be the form of the contact term. This work I did with Rajesh. So just to tell you how the analytic functionals look. So here I'm just plotting this omega, little omega. I can also look at the kind of things that Leonardo and company looked at, but those are much harder because they had a non-trivial integral to do. These are simpler functionals to look at. And this little omega was used to get the epsilon expansion to work in the fixed T dispersion relation. So this capital omega is our version of these fixed T sum rules. The superscript P stands for Polyakov and the superscript W stands for Wheaton. So depending on whether we are expanding using the Polyakov block or the Wheaton block, you get different things. So far as the Polyakov block and the fixed T dispersion relation sum rules are concerned, they are identical. They lie on top of each other. And so far as the Wheaton block is concerned, the zeros, at least in this particular functional that we are looking at, the zeros appear to be at the same place, but the magnitude is different. In that sense, it's a little different. So we have not unearthed what all this means, but let's see. I mean, hopefully there is some benefit, there is some advantage to have in expanding in terms of the Wheaton block. Similar story in d equal to 3. So this was for d equal to 4. This is for d equal to 3. We can do similar things. So let me just conclude. I've gone quite a bit over time, but let me just conclude that using the explicit form of contact terms that we got from this crossing symmetric dispersion relation, we can now understand why this epsilon expansion story that we naively did at the first attempt worked. One can actually show that these contact terms contributed to a higher order. I mean, they would not affect the results that we had found. And since the locality constraints are inbuilt in terms of these Wheaton blocks, it seems like a sensible thing to do, sensible basis to use. But remember one thing, that we still have to impose these locality constraints separately. It's not as if that Wheaton blocks are all that is there and we get no other conditions. You still have to ensure that the spectrum respects these locality constraints. And one thing that we are trying to do is we're trying to see if we can do the S-matrix bootstrap in terms of these Feynman blocks. We have some results. I mean, in the olden days, people did try to put bounds on the amplitude at various values of ST and U, and we seem to be able to get all that quite nicely using this approach. So I think there's more to be done, but thank you very much for listening, and apologies for my overtime.
Thank you very much. Sorry, can you go back one sec?
Yes.
So I thought the Wheaton blocks were obtained from what you call the Polyakov blocks by imposing locality. I got a little confused. Yes. Why do you have to separately impose locality again?
Yeah, because the Wheaton blocks, what we are doing is there are two kinds of constraints. So there are locality constraints and the Polyakov conditions. Okay. So yes, we are saying that. Let me go back to the So let me go back to this one. So the way that we got this expansion is to throw away the negative powers of x. But throwing away the negative powers of x relies on the fact that when we sum over these the full spectrum, these negative powers wouldn't be there in the first line itself. It's just a statement that once we assume that these locality constraints are satisfied, or you assume that the theory is local in the sense that there wouldn't be any negative powers of x, then you would have an expansion of this kind. Because it is this statement, so I'm throwing away these negative powers. So that means that the spectrum is such that the negative powers are not there in the first line to begin with, when we sum over the spectrum. Did that make sense?
Yeah, I'm just getting a little confused why then you have to still impose this condition.
So, okay. So, so see, in the original language, so we had these constraints which corresponded to n minus m being less than 0.
Yeah, these are the same as the null constraints in the language of Simon, or in the language that we had in the paper with him, David and Dalmi. This would be the odd spin function.
Yeah, odd spin constraints. Yeah.
Okay. Yes.
So you would have to, your spectrum has to be such that these are respected. So you have to make sure that these are satisfied.
Yes.
So once these are satisfied, then you're allowed to consider an expansion where these negative powers are not there. So blockwise. Does that make sense? So if I wrote down the full expansion, so if I try to write down, starting from the first line, I try to write down the second line, I would also have plus these odd spin constraints, or these null constraints, or locality constraints. Okay.
Yeah.
So those vanish when we impose. So there would be extra terms in the second line. Those vanish on imposing these locality constraints.
So there are really two sets of functionals: the ones that come from
exactly.
the naive width and expansion, and the separate ones that you have implicitly thrown away, but they're the odd spin ones.
Yes.
Yes. Okay.
Yeah.
Are there any further questions?
So I have a question.
Just
Yeah, Miguel. Yes.
So you're claiming that this prescription of dropping these non-local terms gives you some prescription for the Witten block, where now I can plug in some arbitrary CFT spectrum and the sum over these Witten blocks will converge.
Yes.
It seems quite non-trivial, right? If you pick the contact terms in the wrong way, probably this would not occur.
Yeah, so the convergence statement is the following, that I mean, there is a slick argument and there is a more detailed argument. So both of them, I mean, okay, the slick argument is the following, that if we start with the first line, then I know that this conformal partial wave expansion converges if this A is between this, it satisfies this condition. Now, okay. So the first line, where did it go? Here. Yeah. So the first line, the analog of the first line here, would have the implicitly these crossing symmetric constraints as well, or the null constraints as well, which you would have to check, or the odd spin constraints, whatever nomenclature you want to use. You'd have to check that the sum over spectrum there converges as well. So if the sum over spectrum there does not converge, I believe it converges. We have checked whatever we checked. There's a detailed analysis that we did in the appendix. We checked that it converges, but I'm not. Okay, I think it does. Then the second line will follow. So I think it's an indirect argument, but that's what I mean. I don't have a direct argument because I don't have a general form of the polynomials here, but I think it should work. Dalimir, I can see you. Hi,
Aninda. Actually, I also had a question about this. In your nomenclature, you have these Polyakov blocks, which have this additional non-locality in them. Is there some simple interpretation of this non-locality in the CFT language? Like, for example, in the is it visible in the OPE, or how should I think of this non-locality in the CFT case?
Yeah, I'm not sure. I mean,
I guess it's some extra poles of the Mellin amplitude representing these. Basically, it looks a bit like with an exchange diagram with some extra poles somewhere in the complex S plane. Is that right?
Yeah. I don't have a good physical way. I know what the question that you're asking is. I don't have a good physical way to think about it. Mathematically, of course, I know that the reason why you have these locality constraints is because we have crossing symmetry inbuilt, and then we have to pay some penalty, and the penalty that we're paying is that we have these spurious powers which we have to throw away at the level of the spectrum. And of course, you in the fixed dispersion relation also you have to impose crossing symmetry, and you get this curly E conditions or the odd spin conditions. So that is where I think at least mathematically the equivalence happens. Now, yeah, I don't know physically how to make sense of these spurious powers. Yeah, because yeah.
But if I understand it right, these extra poles would, so in the flat space case, these occur at the pole occurs when x equals 0. I guess x is like x squared plus e squared plus u squared, right? And the same is going to be true in the Mellin variable. So this just occurs at some strange point, in the complex Mellin S plane, where s squared plus u squared is equal to 0. Yeah, okay, so probably there is no nice physical interpretation of these, but they have to cancel no matter what.
Yeah, exactly. I mean, at least you can make some checks. So, for example, it's obvious that if you do it for the dilaton amplitude, you'll see that the sum over things, although each particular term in K, you'll have these infinite number of non-local powers, but when you sum, it's absent. So you can check that they do cancel.
Mhm.
Yeah. So
Yeah. Well. Yeah. Okay. It kind of reminds me a little bit of what happens in the case of the fixed T dispersion relation with subtractions. In that case, the analog of the Witten block, or what I guess we call Polyakov block, also has an extra pole, but that pole arises only because of the subtraction. So I guess it's not really the same. In that case, there's really only one pole. Yeah, it's probably not the same thing, because in that case it has to do with the subtractions, which here you get these poles at x equals 0 even without subtractions. It's really the same thing.
Yeah.
Any further questions? Okay, if not, thank you, Aninda, for a very nice talk. I think finally the situation seems to have been clarified.
Yeah.
And
yeah, thank you.
And yeah, I think in my understanding, the two approaches are completely equivalent.
Yes.
And
indeed, I mean, even these sum rules that we are getting here, I think you should be able to get it from the other approach as well when you.
So you didn't try to quite yet. So one of our main achievements in the paper was to find this
phi2.
Right. The thing that proves the extremality for the spin. And then we had this application to the 3D Ising. Have you tried to do that?
I know what you're talking about. Yes. Yeah. Yeah, we've not reached that far as yet. So.
Yeah. Because of course, I mean, there's not the question that you will have a complete set of functionals. There will be two types: one that come from, in your language, the Polyakov condition; the other that come from this locality constraints.
Yeah.
That will map precisely to the spin even and spin odd functionals in our framework.
Yes.
But of course, for physical application, one of the question is what are what is the positivity? What are the positivity properties of these functionals? And in our framework, it was necessary to form infinite linear combinations in order to get useful positivity property. And the question is whether perhaps you are more lucky or what.
Right. Yeah, that's a great question. So it's something I don't have anything clever to say. We intend to look into that in the next few weeks. Yeah.
Okay. Thank you very much.
Thank you.
Thank you.
Bye-bye.